Derivation of Cp Cv is equal to R. When we heat a substance, its temperature rises under various conditions. For example, the volume may be kept constant, or the pressure may be kept constant, or both may be allowed to vary in some definite manner. In each of these cases, the amount of heat required per mole per unit rise of temperature. We define this as the molar heat capacity is different. Only two kinds of molar heat capacities are different for gases are important for gases, namely that at constant volume Cv and that at constant pressure Cp. Let us consider a piston cylinder arrangement. Having a certain number of moles of an ideal gas, the cylinder is placed on heat reservoir, the temperature of which can be raised or lowered as needed. The gas has a pressure P such that its upward force on the frictionless piston just balances the weight of the piston and its load. This figure shows two isotherms of an ideal gas at temperature T and T plus delta T. Suppose that the gas is taken along the constant pressure path A to B. The temperature also increases by delta T along this path. The heat transferred to the gas in this process is given by delta Q is equal to NCP delta T, where Cp is the molar heat capacity at constant pressure. We note that the volume increases in this process. We call this increase as UME. Increases in this process. We call this increase as delta V. So the work done by the gas is W is equal to P delta V. Applying the first law to this process, we have delta U is equal to delta Q minus delta W is equal to NCP delta T minus P delta V. The temperature of a given mass of gas is raised by the same amount by a constant volume process. Apply the equation of state PV is equal to nRT to the constant pressure process A B. For P constant, we have taking P delta V is equal to nR delta T. Let us consider the constant volume process that carries the system along the path A to C. By definition, Q is equal to NCV delta T, where Cv is the molar heat capacity at constant volume. Also, delta V is equal to O, so delta W is equal to P delta V is also 0. Therefore, from the first law of thermodynamics, Q minus W is equal to delta U. We have delta U is equal to NCV delta T. Substituting this into equation, we get NCP delta T is equal to NCV delta T plus nR delta T, which gives Cp minus Cv is equal to R. This expression applies to any ideal gas. It shows that the heat capacity of an ideal gas at constant pressure is greater than the heat capacity at constant volume by an amount r, the universal gas constant.